Yeah, thank you everyone. My name is Michael Farb. I'm a research programmer here at Carnegie Mellon with Scilab. And my background is in engineering. I've been working with mobile devices and writing applications for them for the last 15 years. And I have the privilege for the last couple of years now working with world-class computer scientists and researchers, Yosun Lin, Tiffany Hyunjin Kim, John McKeon, and Adrian Perrick to build this system. And what we're trying to do is trying to make key exchange simple and still maintain that security, right? So we developed SafeSlinger to do that. And as an overview, I'd like to show you, take 2 minutes of your time to show you from the user perspective risks and the experience of using the application, and then go into a little bit of those risks and how we've constructed the application to defend them.
Send messages over the internet. However, not many people know that attackers can observe and alter their messages. Moreover, this own personal data can cause serious problems, such as spam or phishing attacks. What can we do to protect each person's identity data? We can use cryptographic keys to render the message useless to attackers. We cannot secure the entire internet, but we can secure a small section of it. We've developed SafeSlinger to do just that. SafeSlinger generates secret keys when people meet. That data is combined on each phone, and validation information is displayed as a three-word phrase. When each person selects the same set of words on each phone, the identity data is revealed. This also works the same way in larger numbers of people. It's like handing a card to your business card, printed in invisible ink, and only your friends read it. Whether meeting in person or over the telephone, you have the assurance that the other person is real. SafeSlinger is available for Android devices, as well as iPhones, iPads, and the iPod Touch. We can compose a text message or add an attachment and select one of our secure identities. SafeSlinger will sign the message, encrypt it, and send it through the internet. When our message arrives, it will be encrypted and verified with the key exchange. Now, people can send messages to each other securely. You can be sure that messages are sent only from the same people that you shared identities with, and that no one else can read your messages.
I like that video. That's something, it's a portion of a 3-minute video that we give to end users as a very simple overview to understand the system and what they're protecting themselves against. But let's go into a little more detail. And what I'm going to talk about today is the exchange portion of our protocol, our exchange protocol, not the text messaging. I can do some demos in the break if you want. We can do some exchanges, some text messaging if anyone wants to, if they have their Android or iPhone smartphone. I'd be happy to do that. So this problem is key distribution. It's a fundamental problem in pairs or in groups. We have many useful protocols such as SSL for entities that already share authentic key material. But the root of the problem still remains: how do we ensure and obtain the authentic public key from the intended individual, right? So we might meet in pairs. We might be at a business lunch. We might want to set up a project group for a class. We might want to do some new corporate project, share keys together to establish some shared secrets. So some previous solutions to this key exchange and some that are still in use today, certainly a certificate authority used by a public key infrastructure. In this case, you're trusting a central authority. For the end user, they must be a member of an organization. It takes some money to implement the system. So that may not be the best choice for the end user. PGP is a little more accessible to the end user. However, there's a learning curve involved here. People must know the protocol, how to announce your hash and read it back. It requires a little bit of sophistication, so perhaps not the best choice for the end user for ease of use. One of the potential ideal solutions to a key exchange might be the Diffie-Hellman exchange protocol. So in this case, our goal is to establish a shared secret between two parties for later further use, right? So what do we do to set up the protocol? A sends his public key to, I knew that was going to happen around 10 o'clock. Always back up your system. I was just waiting for it to happen. All right, I think we're back. So A will announce his public key to B, public half key. B announces his public half key to A. And now they can separately construct the same shared equivalent key and then communicate securely. So this might be the ideal solution. The problem is the man-in-the-middle attack. And that's one of the big problems that we want to solve in SafeSlinger. Right? So an attacker is invisible. So if we start a protocol and an attacker has the ability to intercept and alter the message before it continues to B, then we shared A to, we've announced a key from A to M. M can announce a key posing as A to B and do the reverse. So in this case, we've got a secure channel between A and the attacker and B, and the attacker learns all the information in between, right? So the problem here is that the keys that those two sets of parties have are not equivalent. So if we have a way to detect that those keys are not equivalent, we can defend against the attack. So we do that by using an out-of-band channel, right? It's nice to use these wireless protocols to share these large keys instead of having to announce them and read them out, write them down on paper. So we use our in-band channel to make these announcements, as you've seen, but of course we have this attacker who's active and can observe. So we use an out-of-band channel to share the properties of that key to determine if they're different or not, right? We want them to be the same. So we can use a hard cable, NFC, Bluetooth. There are a lot of different ways of doing this. We can announce it visually. We can speak it. So some issues with out-of-band channels are they can be somewhat inconvenient in group settings. They're often set up for pairwise interactions, right? So at a group of 10 people, if we want to support a group from 2 to 10 people, 10, you need 45 interactions. Right? This can take some time. This can be slow. Another attack that we want to prevent against is the group in the middle attack. This is a little more sophisticated. The assumptions here are that all members share a secret, right? All members know the number of members present. But in that case, a malicious group member in red, right? See all the nice Pac-Mans? Right? So he can create a separate group for victim members, right? Creates a sufficient number of visual identities such that each group has the correct number of members, and now the victim members believe that they are part of a group of 4 members with 3 others. But instead, the victim is in a separate group with the adversary and fake identities. So this is another attack we're going to construct a defense against, right? So our goals are ambitious. We want easy to use, and we want high security. We want scalability. Right? We don't want to have separate pairwise interactions in a large group. We want authenticity. We want to be sure at the end of this protocol that everything we exchanged was sent by the exact people we expected. We want secrecy. We don't want to leak any information no matter what communication channel we use. If it's the internet, if it's Bluetooth, whatever it is. We want it to be easy to use. We want to reduce that learning curve that we might have using PGP. We want portability. We want heterogeneous platforms, right? The same device, the same application on the Android should run on the iPhone. These 2 phones should communicate easily together. So one of the ways that we do that is we construct a very simple server that does almost no work, just exchanges messages between parties. Right? And the reason we use the internet is it's the most available to the largest number of Android and iPhone devices, which is our target at the moment, the largest number of smartphone users. Right? Most phones do have Bluetooth. However, there's a technical issue with the original Bluetooth implementation on iPhone. Right? It doesn't like Android. Okay? Wi-Fi ad hoc, NFC are not incredibly widely available. That's changing over time. So we might see a second version of what we have that perhaps doesn't need the internet. But for now, this is the common denominator. So the interactions that we have, we want to be simple. So we have our Android device. We have a couple of iOS devices, Alice, Bob, and Carol. We start our protocol, and they have the option of minimally sending their public key, but also other contact data if they wish, and each user can turn that off. You don't have to share that information, but often it's convenient when you're doing this exchange to also share other properties from your vCard. Each user counts the number of users in the room, pretty simple, right? We use this later to defend against the group in the middle. I'll talk about that. Okay. And then the first of two out-of-band comparisons. Right? Each user is given a low entropy ID, and it's used to group them on the server. Right? We don't necessarily know who is where. We don't want to leak any GPS information or accelerometer data. So we have them play a little game. Everyone gets a number. Everyone figures out, communicates together, which is the lowest. Everyone enters the lowest. It makes it easy for the server to exchange group packets. Okay? So the second interaction is a hash which represents the ordered combination of all the data that we've sent so far. Okay? We're validating each phone should have the same set of data from every member ordered in the same way. If that's true, they will all be able to pick the same phrase. And there's a reason there are two decoys here. We'll talk about that. And so at the end, we just get a decrypted version. Simple if there's a photo, name, we know who we're importing, no one we didn't expect. Right? So we have one number comparison and one word comparison, one word phrase comparison. So we have 4 challenges then, right? When we construct this, we want to prevent private information leaks. Okay. How do we do this? So the server could learn the contact information of all users unless we do something to protect it, since we're using the internet, right? We use a grouped form of the Diffie-Hellman protocol called the STR protocol. I can talk about that in the break if somebody wants to. But it essentially allows you to efficiently, in wireless communication, do that pairwise Diffie-Hellman exchange now that as long as we've first authenticated that all the keys being exchanged are from the people we expect. The second challenge is if we present this hash of all information for people to compare out of band, we don't want them just to click through and click next, right? That's an easy thing to do. We want to construct a way to force them to perform the out-of-band protocol, to out-of-band comparison. Right? So we add those 2 decoys. We don't pre-select anything. We vary the order at which the correct and the 2 decoys are presented. The user must choose something in comparison with some other user to continue. It's hard to read those buttons at the bottom. Sorry about that. They essentially are next or no match. Challenge, the third one is that we don't want to reveal any information if the protocol fails. If there's an attacker present in our exchanged sets of keys, right? That's going to show up. We're not going to find the same matching set of 3 words on all phones, right? So the user that determines that should be able to announce that to the rest of the group. We don't want any private information revealed. This should be all or nothing, right? We want to make sure that we get to the end of the protocol fully authenticated with everyone admitting that everything matches. So we do that by constructing our commitment tree with 2 nonces, one to determine, yes, I have a correct match or a nonce n, and one to show that I had an error. I did not find a match. We start with our data encrypted by this nonce match, and then a Diffie-Hellman public key will construct. Right? And we think of our protocol in 3 phases. One is the construction of this hash. The next is stepping through it to verify that all elements of the hash are what we expect. And the final is sending this nonce M, which is used as a private key for each user so that we can decrypt it, decrypt this data, this vCard data. Right? So we keep constructing our commitment tree. We first announce our commitment to the group, the next 3 pairs of information, verify it equals the commitment. We can use this now and order those 3 pairs of information on every phone, since every user has it, construct our 3-word phrase, display it to the user. They now can make a choice. They can choose to say, I did not find a match, and reveal the 2 pairs of information that belong to that choice, or that I found a match, and it can reveal those 2 pieces of information. It's important to note that we've not yet revealed the private key. But once everyone has made a choice, we can do that. We can take this Diffie-Hellman public key that we've already shared, construct using the SDR protocol, the same Diffie-Hellman private key, Diffie-Hellman secret, and use that to encrypt the private key, which we can then share with everyone and decrypt each person's data. So the last challenge is this group in the middle attack, where malicious group members perform this group in the middle attack. So the users enter the number of participants as one of the approaches, right? We only want to accept the exact number of pieces of user data we expect. If we have 3 people, we don't want 4, right? If we get 3, one of them could be from an attacker. Of course, that is going to make the hash different on each phone, and we can detect it. All users will compare the word list with other users, and showing 24 bits of our 250-bit hash between all users, it's difficult for an attacker to come up with an equivalent hash that would that they could present on someone else's phone. A little bit of comparison if you've used Bump before. We've done some user studies. We chose Bump just as it's the other major application used to exchange contact data. You bump your phones together. Some differences are we designed our for group. Theirs is designed for pairwise interactions, so it becomes cumbersome to use it in groups. I have some results from our user studies which show that. We have the addition of being able to announce this group ID and this hash, say over a landline if you're using your cell phones. So we can actually perform this remotely. We can't do that with Bump. With each, since both protocols use TCP/IP to communicate with their respective servers, of course you can learn the IP address of any user, but we don't reveal any location data, GPS, accelerometer information. We already have quite high security properties compared to Bump. The device requirements are simply an internet. I might need a GPS and accelerometer data if I use Bump. So we might be able to implement SafeSlinger on more platforms. And we add the additional feature of this built-in secure messaging. And it's also fun to use, although Bump is kind of fun too. Okay. So you can see when we did our user study, both protocols for our 2-user exchange come in under 30 seconds. Now when we start to add more members, those numbers start to degrade pretty quickly, mostly due to collisions. If you're bumping with several people in the same room and it's pairwise, it gets confused. It doesn't know exactly who wants to exchange data, so you often get someone from across the room data at the same time that you're trying to get the person next to you. Right? That can happen. And so as an overview of our system, we maintain our user privacy. Only group users learn the exchange information. The server doesn't learn the information. The server could be malicious. We're protected there. It's a simple protocol to use and resilient to user errors. We have the addition of on top of this exchange, now we implement the actual use of these public keys. We create a simple text messaging application. And we also create this feature called secure introduction. So we can leverage our file transfer mechanism to share a one-hop extension of trust with anyone that we've already exchanged keys with. If I've exchanged with Bob and Carol separately on separate occasions, I can send their public key to each other and they know the message was sent from me because we've verified our identity already. The application is available to use. The webpage there will give you links to our paper, as well as some installation instructions. This little QR code, which you probably can't scan because it's cut off, but it will take you to a mobile version of our installation page. And for our next steps, we're working now to open source the product. We wanted to know from all of you how best to integrate it into existing products, as well as working on developing plugins for instant messaging and email and things like that. And I think that's what I have. If anyone wants to ask a question.
Any questions for Michael?
I have one, Mike. Go ahead. What is the encryption algorithm you use for the actual messaging? Is that AES?
Yes, and actually, my partner did the implementation to it, and I forget the exact order in which direction we did it. I think we encrypt, sign, then encrypt. One of them was better for performance rather than sign, encrypt, sign.
Okay.
But I could get you details on that. I think we have them in our paper as well.
And the key size for the AES, is that 128 bits or?
2048.
Sorry?
2048.
Okay. And with that you get 20 seconds.
Yes. Well, and you're talking about the exchange. So that is, I thought you were talking about the actual messaging service.
I can imagine that creating larger keys for the actual messaging also, the larger the keys also, the more time it takes for the protocol, or is that not what is the most time consuming?
The exchange is 256 bits. Mm-hmm. Messaging is 2048.
Okay.
Yeah.
So in what you're demonstrating here, the principles involved are each able to perform operations and are thinking individuals. Could this be extended to facilitate one or more of those parties being a machine instead of a thinking individual?
We're still thinking about that. I guess it's the question of level of trust, right? It's a little easier to assume that someone you know is, or perhaps not. I mean, I could see a way that could be constructed, right? So if I trust a company that might implement this as a machine, and I'm a user using it, the same level of impetus to do well is there, right? I have a reputation to protect, whether I'm a person or a machine, yeah.
Have you been discussing this idea with the video or FIDO alliance? Because it's basically about user and machine authentication.
I don't know if I understand your question.
Have you been discussing this idea with the FIDO alliance? So we are looking into using, for example, hardware tokens for user authentication.
Okay, so we're working on other tokens to use as user authentication?
Well, there are many parties looking into that kind of solution. Like Wall is also investigating that, where you basically have from hardware USB stick or NFC token, which can do crypto for you, which can contain big public keys. Still, we then have the question, how do you exchange that key? So we have to be looking into that, so that this
Okay.
is all part of the problem maybe.
Right. I mean, one potential is, if we use something like NFC, so we could provide the same level of security, but in NFC we already know some properties, right? We know it's pairwise, so we can eliminate, people don't have to choose how many people. We also don't need to add that grouping number. So really, when you start the exchange, you just get this hash to compare out a band. A little simpler. Future work.
So I have a question. If I have a malicious server and you got 4 people in a room, they're not allowed to talk to each other, they can see each other.
Okay.
The malicious server injects a fake person into the system and deletes numbers for people.
Right, so fake number 5, right?
Sorry.
A fifth person, a fake identity.
Yeah,
Yep.
it's actually somebody sitting at a keyboard 5,000 miles away. What stops that from working?
So each user, and they can see.
Not talk to each other, they cannot say anything to each other, they're totally clear.
Well, it doesn't work, right? You need the people that are communicating, intend to communicate, all need a way to out-of-band communicate.
Right. So it breaks because they can't talk to each other.
Right.
Yeah, Mike, I was just wondering if you could mention where you're seeing interest for this, as well as the conference you're going to be going and talking.
Yeah, I'm sorry, I didn't mention it. So the paper based on this application and the Exchange protocol is being presented on Thursday at the MobiConf conference in Miami. I forget where I'm going this week. And I really need to pack shorts, I think, from what I hear. So that's going on right now. Various levels. I could tell you that we've recently seen a spike of users in Taiwan. And I think there's a background story there. I wouldn't mind telling you offline, but so a lot of the current user base is US, and that's all I can really tell from the. I can just tell who's in, which countries have installed it, not who. So.
I have a question. So the purpose is usability as well, in your numbers. Did you account for the amount of time it would take 10 people to say, okay, we're all gonna do it together, quit talking, come over here to this side of the room? It is a usability tool. You said security goes up as a group size, but also the ability to herd the cats into one room increases as well.
Right. Well, you see that here with 8 users. All those users had to communicate, and this is an average. Right? They all had to communicate those numbers, and it didn't increase comparatively. It's still within a minute.
And the end result is they've each exchanged point-to-point their own public keys, or is there a group public key? Is the group out just for the exchange, and then they each give their own?
They've each exchanged their separate public key with each other member of the group. Yeah.
Thank you.
So 1 interaction versus 45 for 10 for a pairwise.
Is that persistent? Does that continue on indefinitely, or do you have to rerun this every time you want to communicate?
It's a long-term key, right? If you want to update your key, you run it again. We're also implementing update and revocation protocol to the text messaging to make it easier for people to do that.